Hello students, welcome to this lecture on multiplexer. We will see the multiplexer representation in two forms, one using the transmission gates and another one using the tri-state logic families. Right. Moving ahead, so this is the transmission gate configured multiplexer circuit, and it's a 2:1 multiplexer. And I have represented it in a very simple manner. So let's say that let me pick up a pointer. Let's say when S is 1, when the select line is 1 here, so I will have this transmission gate passing in the input to the output Y. Right? If S is equal to high, S bar will be low, and so this particular transmission gate will be working. This particular transmission gate won't be working because this S bar is connected to the NMOS here, and then S is connected to the PMOS. So when S is equal to 1, this will not work. Only when S is equal to 0, this transmission gate is going to pass the input to the output. So what happens is when S is equal to 1, we will have whatever is the input here will be passed to the output, and the input here is nothing but the inverted. It's basically the inverter output of the signal A. So I will get when S is equal to 1, the output will be nothing but A bar. And then when S is equal to 0, the output will be B bar. So this is one form of building the multiplexer circuit, 2:1 multiplexer using the transmission gates. The another form of building the multiplexer is the tri-state multiplexer. So the tri-state it has basically the mirror topology and not the conduction complement topology. So the mirror topology means whatever we have the circuits in series on the pull down side, the same series of the transistors will be there on the pull up side. So here A is given to the PMOS transistors and to the NMOS transistor, which are closer to the rail, and the select signal is given to the PMOS and NMOS transistor, which are closest to the output node. Right, so when A is equal to 1 in this particular case, or rather, so when the select is 1 here, when S is equal to 1, this will be on, and then this will be on because S0 will be 0, and then this PMOS will be on. And so the output will be nothing but whatever is the based on the A, the output will be nothing but A bar, the complement of the A signal. When S is equal to 1, I said this will be on and this will be on. Right, this particular transistors which are there on the next leg or the next branch, this particular transistors will be off, and thereby Y will not be connected to the transistors connected to the B. Right, so Y will be connected only to the transistors of the A transistors on the PMOS and NMOS side, and it will give me the complementary output of the A signal. When S is equal to 0, this one will be on and this one will be on. S will be 0, S bar will be 1, and then the NMOS transistors here will be on, and then S will be on here. So Y will be the complementary, it will be a complement of the B signal. And these two transistors will be off, and thereby Y will be disconnected from the A transistors. So when S is equal to 1, I will have, so the Y output will be nothing but when S is equal to 1, I will have an A bar output, and when S is equal to 0, so that means S bar into B. So we will get this particular expression. Very similar. In fact, it is same as that of this particular expression. Although the circuit, the schematics or the circuit design is different. So one is from the tri-state family, and another one is the transmission gate family. Hope this is clear. So what I've done here in this particular slide is I have drawn the stick diagram, basically the layout for the transmission gate, CMOS transmission gates configured MUX multiplexer circuit. So let's have a look into this particular stick diagram very closely. So in this particular stick diagram, so I'm going to pick up the transistors A and B, basically the inverters A and B. So the inverters A and B here, so 1 and 2 I'm going to pick. So I'm going to talk about 1 here first. So in this particular stick diagram, the A is nothing but given to the polysilicon gate. So this is the polysilicon gate. And on either side, I will have the diffusions. On the either side, I will have the diffusions. One diffusion on the PMOS side. So if I consider the PMOS diffusions and NMOS diffusions, I will have the polysilicon gate, and on either side I will have the diffusions, drain and the source. So one is connected to the source of the PMOS transistor is connected to the VDD. The source of the NMOS transistor is connected to the ground rail. Right. So here I want to emphasize that the PMOS, the P diffusion and N diffusion represents that wherever you will see a polysilicon gate, that represents an NMOS transistor on an N diffusion line. And similarly, on the P diffusion line, wherever we see a polysilicon gate, that represents one PMOS transistors on the P diffusion line. So in this case, the A is cutting here. A is cutting here, so that means that I need to have the diffusions to make the NMOS and then the PMOS transistors complete. So what I've done is, on one side of the diffusion, it is connected to the VDD, the another side it is connected to this particular N1 node. Right. Similarly, for the NMOS transistors on the N diffusion line, one diffusion is connected to the ground, the other diffusion is connected to the N1 node. And this N1 node are connected together, right? Because it's an inverter. So the PMOS transistor diffusion and then the NMOS transistor diffusion are connected, and that is this particular metal line. So this particular realization of this inverter onto the stick diagram is complete. Let's go to the this second inverter, which I've drawn it at the end here. So a B polysilicon line cutting the P diffusion and N diffusion. On one side of the diffusion it is ground, the other side of the diffusion of the PMOS it is VDD, and the other side is connected to the N2. So this is the N2 line, which is a metal line, which is connected here. So these two inverters are done or realized in the stick diagram or in the simpler representation of the layout. Let's go to this particular transmission gate. In this particular transmission gate, I have two transistors, NMOS and PMOS. PMOS is the PMOS input or the PMOS gate is connected to the S bar, and NMOS gate is connected to S input, right? So what it means is, on the P diffusion, if I should have an S bar polysilicon gate, on the N diffusion, I should have an S polysilicon gate, right? So I have an S polysilicon gate and S bar polysilicon gate, S bar on the P diffusion side and S on the N diffusion side. So once I have that, I know the diffusion side is N1 here. This is N1 point, and on the other side is the Y point. So on the either side of S bar, it is N1 point, and then the other side is the Y point. Similarly, for the N diffusion, S polysilicon gate, one side it is N1, the other side of the diffusion is Y, and that's what I have represented. S polysilicon gate, one side it is N1, the other side is Y. The Y's are, this particular point Y is actually connected. So the diffusions are connected, so that's why I have this Y. So this is a Y metal line. And let's talk about this particular transmission gate. This particular transmission gate, if you look closely, this S bar is going to the NMOS transistor and S is going to the PMOS transistor. So I should have an S bar polysilicon gate for the NMOS transistor. That means S bar cutting the N diffusions, and S as the polysilicon gate connecting to the PMOS transistor. So S is now the polysilicon gate on the P diffusion lines. So creating two diffusions. On one side it is the N2 one, and other side it is the Y for both the PMOS transistor as well as the NMOS transistor. So S and S bar, on one side it is Y signal, the other side it is N2 signal. So that's what it is represented. So this completes the stick diagram representation of the CMOS transmission gate. Right, this CMOS transmission gate derived multiplexer circuit. Right, hope this stick diagram is very, very clear. It is very interesting to see the stick diagram of a tri-state multiplexer. The tri-state circuit diagram is given here, and there are there are 8 such transistors. Right, so what it means is basically I should have 8 such polysilicon gates, 4 polysilicon gates on the P diffusion lines and 4 on the N diffusion lines, right? So that we will get 4 transistors each on the P diffusion and then the N diffusions. right? If I go back to the previous slide, I also had 4 polysilicon gates on the N diffusion and P diffusion lines, creating 8 such transistors. And why 8? Because this is basically 2 transistors. This is basically 2 transistors, and then this is 2 transistors, and then this is 2 transistors. So total 8 transistors. So same thing we will see in the tri-state multiplexer also. We will have 8 transistors, 4 on the P diffusion line, 4 on the N diffusion lines. Right, so let's look into the first branch, the transistors A, or rather the transistors which are connected to the A signal. So this particular, if I pick this particular transistor on the P diffusion line, the polysilicon gate is nothing but A, and on one side it is connected to the VDD, the other side it is, this is this N1 node, right? So that's what I have written, N1 node. And if I pick this particular transistor now on the NMOS side, on the N diffusion side, I have the A polysilicon gate, and on one side it is, I'll write it as N1, and on the other side it is the ground, right? So this is completed. And similarly, I can complete the B transistors here, on the B polysilicon gate. On one side of this particular diffusion, it is connected to VDD. The other side it is, and on the NMOS side, it is connected to the ground. The other side of the diffusion is, I can write it as N2 and then N2. Right. Note that N1 and N2 are not connected here in this tri-state multiplexer. Right. So if I go back to the previous slide, N1 here was actually connected, right? N1 and N2 are connected in the sense the output of the inverters, which is the output of the inverters, this one in the stick diagram. So there, on both the diffusions of the P diffusions and the N diffusions has to be a single point in the schematic. That means there is a wire that is connecting the PMOS diffusion and NMOS diffusions, right? So N1 was actually connected between the PMOS and NMOS diffusions. Similarly, N2 was connected between the PMOS and NMOS diffusions. And if I look closely now into the tri-state multiplexer design and its stick diagram, the N1 is an unmerged diffusion, or rather it's a merged uncontacted diffusions. Here, the diffusions are merged. So the diffusion of this particular transistor and this particular transistor are actually merged, but there is no metal line, right? Whereas in the previous case of the transmission gates design multiplexers, you can see that the transistors A here on the P diffusion side and on the S bar, so this one, so I'm talking about this particular transistor, and then I'm talking about the inverters PMOS transistors. So this particular line, so let me draw this. So this particular line is a merged diffusion because there are 2 transistors and the diffusions are merged. Even then the diffusions are merged, there is a contact here. So the metal line is going around. That's why it is called as metal contacted merged diffusions. Whereas here, we don't have any metal line that is passing on from N1 to N2. So it is an uncontacted, right? It's a non-metal contact, but it's a merged diffusions, right? And it is merging with that of the S bar signal here. So S bar signal that is having a merged diffusion with that of the A transistor and S bar transistor. So I have an S bar polysilicon gate. On one side it is N1, the other side it is the output Y. Similarly, for the S signal, S transistor on the NMOS side, I have a polysilicon S. On one side it is N1, the other side it is Y. Now remember that the Y's are connected here, right? Y's are connected here means it is indicated by a point here on the PMOS transistor and the NMOS transistor. So that means that the Y has to be connected. So there is a metal line that is going around, right? Going and connecting this particular point and then this particular point. And to complete the other part, we have anyways completed the B transistors. So we have to complete the S and the S bar. So I have an S on the PMOS side. So S, and on one side the diffusion is N2, the other side it is Y. And similarly S bar polysilicon gate, on one side it is N2, the other side it is Y. So this completes the stick diagram. And if I look closely into this particular stick diagram with respect to the previous one, the only difference here is this particular contact line is missing. Otherwise, the tri-state derived mux is also having a similar stick diagram as that of the transmission gate derived multiplexers. The only thing which is missing is the dotted lines, which is the metal lines. So that's what I've written. Nodes N1 and N2 are not connected in this layout compared to the other designs. So the transmission gate multiplexer and then the tri-state multiplexers, the schematic I have designed, we notice that the stick diagram is different by only one metal contact. So the stick diagram, if I actually connect the schematic with this N1 and then N2 connection, this behaves very, very similar to that of the CMOS transmission gate designed multiplexers. Right? Now, what is the advantage of this? So if I actually, this is a tri-state design, but now I am connecting this N1 and N2 nodes. So that means that this now behaves like a transmission gate multiplexer. Right? So because it is behaving, although I have drawn this like a tri-state logic family, but because of this connections between N1 and N2, right? N2 connected to the N2 here and N1 connected to the N1 here. So this, the stick diagram of this represents the transmission gate multiplexer. And so this is now a transmission gate multiplexer. And in a transmission gate multiplexer, I wanted to find out what is the delay. Right? So if I look, if I size it properly, 4422, so that I'll get the switching resistance of R and then R here on this branch on the pull down side. And 4 and 4 will give me the switching resistance of R on the pull up side. So the TPDF will be nothing but as I've calculated here. So the capacitance seen at the output node will be nothing but 4 plus 2 plus 4 plus 2, which will be nothing but 12C. The capacitance here will be nothing but 4, which is a merged capacitance from these two transistors, and then one more 2C merged capacitance from these two transistors. So 6C will be the overall capacitance. And if I want to find out the propagation delay falling, it will be nothing but 12C. And then now we will have this resistance and then this resistance in parallel. And then it will have a in series resistance of R by 2. So I will have an R by 2 and R by 2 in parallel because this node and this metal node are the same now. And this side it is nothing but Y. So I will have a Y line and the switching resistance of this and then this will be in parallel with that of in series that of 2, the R by 2. So that's why I have R by 2 parallel R by 2 plus R by 2. And then the 6C resistance multiplied by the R by 2 as the switching resistance. So overall, I'll get 12 RC. TPDF or rather TPD rising, the propagation delay for the rising will also be very, very similar. So 12C multiplied by 3 by 4R. So there I'll get this particular, this switching resistance in parallel with this, and then finally 6C capacitance multiplied by R by 2. So I'll have 12 RC. So this is the delay for the transmission gate multiplexers where the N1s are connected on both the PMOS and NMOS transistors and N2s are connected on the PMOS and the NMOS transistors. So for a tri-state based multiplexers, what should be the delay? Tri-state based multiplexers means this particular nodes are not connected. Alright. So in that case, I will see a total capacitance of 12C. There will be a capacitance of 4C here and 2C here. I can similarly draw it here and here. But let's say that, under, this particular branch we are interested in. So, so for the propagation delay falling, I will have this 12C multiplied by, the resistance of R. So this transistors and then this transistor will give me a resistance of R. And then this 2C will be multiplied by R by 2. So this 2C multiplied by R by 2 is this one. And then this is a 12 RC, which is output node capacitance multiplied by R. Remember that even for the falling one, this S is equal to 1. That means this transistor is on. Right, this S bar will be 0, and then this transistor will also be on. That means this 4C capacitance will also be considered for the falling output, and as per the Elmore delay method, 4C multiplied by the shared resistance of R, right, should be accommodated. So that's why we have this 4C into R. Total is 17 RC, which is greater than the 12 RC, right? And similarly, TPDR, so that means the propagation delay for the rising one will be nothing but 12C into R multiplied by 4C into R by 2. So this is this, and then this is this. And then this 2C will also come into picture, multiplied by the shared resistance of R. So I will have 16 RC, right, and then 17 RC. Right, again 16 RC is also greater than that of the 12 RC, which we had seen for the transmission gate derived multiplexers. Right, so this is a very small analysis on the multiplexer design. So we have two different multiplexer designs. One is the tri-state based, and another one is the transmission gates. The tri-state based multiplexers, the layout of both of them will be very, very similar. The advantages with the tri-state multiplexer is the metal line is not there. So additional two metal lines doesn't come into the picture. So which is good in the sense that additional metal lines will cost us a little bit more. But whereas the delay in terms of the tri-state multiplexer, it is more than that of the transmission gate, because the metal line is connecting, and then it makes the switching resistance less, because the switching resistance, the equivalent switching resistance for the two transistors which are in parallel, it reduces the switching resistance, and thereby the delay will also naturally be smaller.